Morning, everyone. This is lecture 19, Design Exercise 5. I'm Sundar Atre, your instructor for ME 575, Design to Manufacture Digital Tools. Today, we will look at certain extensions of the concept of shape factors, applying them to complex structures. Complex by way of magnitude, complex by way of being either extremely large, and we'll take bridges as example. Alternatively, something that's extremely small. We'll take a bunch of bio-inspired structures in the microscopic or submicroscopic scale as examples. Look at these two types of bridges. They're made of completely different materials, have different span lengths, different heights, most likely very different structural attributes based on what load they can carry and how much they might deflect under that load. This allows us to explore and extend the concept of shape factors to these entirely different shapes. Let's review experimental shape factors for a few materials: alloys, composites, plastics, and naturally occurring materials. And you see that the shape factor at a maximum is higher for a given material in bending compared to torsion. So this is one type of a given. Do you remember what it is that aluminum offers as a maximum in bending and torsion? Keep in mind these values of 44 and 31. And let's move forward with some experimental stiffness data. You are given the beam stiffness, you're given a mass per unit length, given the length of the beam, right? Given some beam material, you're given some material density and the modulus, in this case pertaining to the 6061 aluminum alloy. We have earlier on derived this equation for minimizing mass as a product of a structural factor in the design, a dimensional factor in the design, and a material factor in the design. And we decided that we could take into account some shape factor by incorporating it into the material factor. So if you know all these, you can find the mass and the minimum mass. Right? To minimize this mass, you would look to minimize this overall quantity or maximize the reciprocal of this quantity. Let's see this in practice. What values have we been given? Right? And how do we look at understanding some things, right? So what is missing over here? If you see, phi is not given. And so if you rearrange terms, you will be able to derive an expression for the shape factor in the bending mode. And so you basically take all these terms to the left, bring the mass to the right denominator, square everything on both sides, and you get this term over here. If you take C1 as 48, you can compute phi B as 18.6, knowing the length, knowing the stiffness, knowing the modulus, knowing the density, knowing C1, and knowing the mass per unit length. The question to you is this the maximum? So for an aluminum alloy, we know that in bending, you can maximize a shape factor to 44, right? So clearly the shape that we're looking at is well within the bounds of what was technically possible with aluminum alloys.